Hi, my name is Michael Hitchman and I'm with you today to talk about the operation of bipolar junction transistors, more commonly known as BJTs. BJTs are constructed as layers of semiconductor materials, usually silicon, doped with suitable impurities. Different types of impurities are used to create N-type and P-type semiconductors. In N-type material, conduction is mainly due to negatively charged electrons, whereas in P-type material, conduction is due to positively charged holes. Our NPN transistor consists of a layer of P-type material between two layers of N-type material as shown in the figure. Each PN junction forms a diode, but if the junctions are made very close together in a single crystal of the semiconductor, the current in one junction affects the current in the other. It is this interaction that makes a transistor a particularly useful device. We call these layers the emitter, the base, and the collector. From the previous slide, we saw that the BJT is similar to the operation of a valve in a fluid flow system. In suitable circuits, if a small current is made to flow into the base terminal, a much larger current flows into the collector and out of the emitter terminal. We can imagine that the base current opens a valve between the collector and emitter. Larger base currents open the valve wider. When a signal to be amplified is amplified as a current to the base, the valve between the collector and base opens and closes in responses to changes in the signal. Thus, a current with magnified fluctuations flows between the collector and the emitter. With this analogy, we can see that a BJT can be used as a switch and as an amplifier. A PN junction is forward biased by applying voltage with positive polarity on the P side of the semiconductor. On the other hand, reverse bias occurs if the positive polarity is applied to the N side. In normal operation as an amplifier, the base collector junction is reverse biased and the base emitter junction is forward biased. We can then use the Shockley equation below to gain the emitter current, IE, in terms of the base to emitter voltage, VBE. Of course, Kirchhoff's current law requires the current flowing out of the BJT is equal to the sum of the currents flowing into it. There we can derive the following equation, IE equals IC plus IB. If we define the parameter alpha as a ratio of collector current to the emitter current, which is displayed as alpha equals IC over IE, values for alpha range from 0.9 to 0.99, with 0.99 being the typical value. This leads to another important parameter of the BJT, which is beta. Beta is a ratio of the collector base to the base current. The values for beta can range from 10 to 1000, with 100 being typically found in most common transistors. This parameter is very useful because it basically tells us how much we can amplify our input signal without distortion. So far we have only considered the NPN BJT, but an equally useful device results if the base is a layer of N-type material between two P-type layers. For proper operation as an amplifier, the polarities of the DC voltages applied to the PNP device must be opposite of the NPN. Furthermore, current flows in opposite directions. Apart from these differences, the two different devices are nearly identical. For the PNP transistor, we can write the following equations on the right there, which are exactly the same as for the NPN transistor before. As previously stated, when used as an amplifier incorrectly, the output waveforms can become distorted. To function correctly, the transistor must be in the active region of operation. This phenomenon is usually demonstrated when the input is a sinusoidal wave. If the troughs of the waveform dip too low, the bottom of the output can be clipped, as the BJT has been driven into the cutoff region. Inversely, when the BJT is driven into saturation range, the top of the waveform cannot be represented correctly, which results in a clipped waveform. This relates back to the beta parameter discussed before, which gives an indication of the limitations when used as an amplifier. For the relevance with our team project for ENEG12006, with the water tank control circuit, we can use BJTs to operate the solenoid relays like a switch. The following figures show how a PNP or NPN transistor can be utilized as a relay driver. The implementation of this subcircuit allows the control of the required relays with very minimal power. The PMP circuit uses an active high, which means the logic delivers a high voltage to the base terminal. The BJT will then turn on and activate the relay. The NPN circuit uses an active low, so the BJT will switch on when the logic delivers a low voltage. Each circuit has its own benefits, so each can be utilized in a team project depending on your design philosophy. Thank you for watching. Hope you enjoyed the presentation and look forward to your feedback. Thank you very much.